Welcome to PECO Virtual School. My name is Wanda Ronald and I'm a teacher of physics. What we are going to study today is measuring area. Before we continue, in our previous lesson we looked at measurements and we looked at physical quantities. There are basic physical quantities and there are derived physical quantities. We saw that length, time and mass are basic, and others like area, volume, density and so on are derived. And then we looked at length as a physical quantity, how it can be measured, and now we are going to look at area. Now area is a quantity that expresses the extent of a surface on a given plane or the amount of space covered by the surface of an object. The amount of space covered by just a surface. Let's look at this figure. This is a rectangle. This rectangular figure here is covering a certain space. Now the space which is occupied by the surface is the area. Look at a circle. A circle also covers a certain space. On its plane, this surface here is called a plane, and the space covered by the plane or by the surface is the one we look at, we call area. There are many shapes. Triangle, like this triangle here. There is this star. This star is also covering certain space. Now these are shapes that are regular, they are uniform, they have defined shape, but there are those whose shapes are not defined, like this one here and this one. For example, this one looks like a cloud and the shape here is not defined. You cannot call it circle, you cannot call it rectangle, you cannot call it a triangle. So but the surfaces, their surfaces are covering a certain space, and that space is what we call the area. Now area is a physical quantity derived from length, as we shall see. Area is measured in square units. Now the SI unit of area is a square meter or meters squared, as commonly read, but we read this as square meter. But there are other units of area. For example, if I even list all of them, you can try to mention how square kilometer, square miles, bigger units, square centimeters, square millimeters, square feet, for example for land, which is measured in terms of feet, the width feet and the length in terms of feet, so we shall get square feet, and many others just to mention but a few, just to mention but a few. So having known the units, how are they converted? How do we convert from one unit to another? Let's look at an example. Express each of the following in centimeters squared. For example, you have 7.5 meters squared or 4.2 meters squared, or 0.09 meters squared, or 0.0007 kilometers squared. How can they be expressed in centimeters squared? So we're going to look at that. Okay, so looking at the first one, 1 meter, how many? 1 meter is equal to 100 centimeters. Now if I want a square meter, it means I will square the 1 meter. This one, so 1 meter times 1 meter, which comes to 100 centimeters times 100 centimeters. So 1 meter squared is equal to 10,000 centimeters squared. Now how about if I have 7.5 meters squared, then I'll have, if 1 is equal to 10,000 centimeters squared, how about 7.5? So we shall multiply by 10,000 centimeters squared, and therefore the answer will be 75,000 centimeters squared. This is our first example. Let's look at our second one. Of course, that will now be easy. 4.2 meters squared, then you shall say 4.2 times 100 times 100, which is the 10,000, and we get 42,000 centimeters squared. Moving faster, similarly 0.09 meters squared. So we shall get this 100 times 100, which is the 10,000 we get here, and multiply by 0.09, and the answer will be 900 centimeters. Please cross check with the answers. Okay, how about 0.00007 kilometers squared? Now from kilometer you have to first change to meters, then from meters then you change to centimeters. But now remember that 1 kilometer is equal to 1,000 meters. So if it is squared, then we shall square the 1,000 by multiplying 1,000 by 1,000, and then 1 meter squared is equal to 100 times 100 centimeters. So at the end of it all, we shall have multiplied this figure by all these, and we shall get 7,000 centimeters squared. So you first convert, you can do it independently, convert the kilometer squared to meter squared, then from meter squared to centimeters squared. Okay, so that is simple conversion, but you will do more exercise on that. Express the following areas in meters squared. If I have now from centimeter squared to meters squared, let's look at these two. Now we just saw above that 1 meter squared is equal to 10,000 centimeters squared. Okay, 1 meter squared is equal to 10,000 centimeters squared. So how about if I have 4,000, then I need to divide by 10,000. If you are changing from a smaller unit to a bigger unit, you have to divide by that factor. So now the factor is 1 meter squared is equal to 10,000 centimeters squared. So the 4,000 centimeters, if I'm now moving from this side to this side, then I have to divide by the 10,000, and the answer will be 0.4 meters squared. The second question, 0.07 now will be 0.07 divided by 10,000, and we shall get 0.00007 meters squared. So they are converting from centimeters squared to meters squared. Now, how is area measured? How do we measure area of a surface? Now we have regularly shaped objects. The area of regularly shaped surfaces such as rectangles, triangles, circles can be obtained by applying an appropriate formula. by applying an appropriate formula. And by at this level, you left primary, you know those formulas, as we shall see in the table below. So the table below shows some regular shapes and their corresponding formulae for area. So here we're going to have a table which shows the shape of the object or the shape of the surface and the formula for area. For example, let's start with that shape, and that shape is a rectangle. This shape here is a rectangle. What's the formula? I guess you know that very well. Formula A is equal to the length times width, which you can simply write in L times W. Length times the length times the width, L times W, or simply LW. Let's have a triangle or triangular shape. What is the formula for its area? Okay, this triangular has base and the height h, the base B and the height h. How do you get area? Area A is given by a half into bracket base times height, or simply a half times B times h. Okay, or a half times B times h, or a half B h, where B is the length of the base and h is the height of the triangle from the base to the peak here. That you know very well. Let's look at another shape, which is a circle. Okay, the circle has radius r, and the formula for that you know very well is pi r squared. Pi r squared, where this value of pi is 22 over 7, or simply 3.142. Another shape we look at is a trapezium. With this length B, the upper length A, and the height what? H. What is the formula for its area? And remember, it is a half times, or put in bracket, A plus B, close the bracket, H. A plus B. It means you first add the value of this length plus the value of this length, first add them before you multiply by h and multiply by a half. Now these are the regular surfaces that do have a defined shape, and you can just determine the length of the sides and use the formula to determine the area of these shapes or these surfaces. How about, how do you get the area of the irregular surface, irregularly shaped surfaces? Now this is simply done by estimation. An estimate of an area of an irregular shape can be done by dividing it into squares, each of area 1 centimeter squared. Now let's look at an example. Estimate the area of the irregular surface shown below. Now if we have this irregular surface here, now we get a graph paper which has squares, and we have said that each square here is 1 centimeter squared. Get a graph paper which has squares and each square is 1 centimeter squared. Okay, then we are going to count the full squares. We're going to count the full squares. Okay, so in our solution we need to get the number of complete squares and get the number of incomplete squares, and we shall divide the number of incomplete squares by 2 and the number of complete squares we shall add. So if I'm to take you back to this, these are the full squares. So 1 2 3 4 5, 1 2 3 4 5 6. So if I multiply this by this I get 30. So these are 30. Then I go the other one, 1 2 3 4, that's now 34. 1 2 3 4, 38, and there is one here which makes 39. So there are 39 complete squares. After having counted all the complete squares, then you go to those which are not complete. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30. So the incomplete squares are 30. Now when you got the number of complete squares are 39 and the number of incomplete squares are 30. So you first divide these incomplete squares by 2, you get 15, and get the number of complete squares to be 39 plus 15, which you got here, and you shall get 34 complete squares. So the estimated area therefore is 54 times 1. So the number 39 plus 15 shall get 54, and you shall get 54 times 1 and you get 54 centimeters squared. Now we call this an estimation because you cannot accurately determine the area of an irregular object. So by estimation we have roughly got the area of that surface we saw above as 54 centimeters squared. Okay. Before we look at measuring volume, so we have looked at area and how area can be determined for regular objects and for irregular surfaces. Now you will get, if you have enrolled for this program for PECO Virtual School, you're going to receive an exercise which will help you to test yourself on converting units. The work will be marked and you'll be given a feedback. And if you have not enrolled, please contact the numbers that you appear on the screen so that you get enrolled and you get a full package other than just watching these tutorials. Good. Another physical quantity we look at is volume. Volume. What is volume? Now, volume is the amount of space occupied by matter. Now, the amount of space is confusing. Area, we say the amount of space, but we said occupied by the surface by the surface of the plane. But here now I'm saying the amount of space occupied by matter of an object. What is in that object, or what is in that body, is called matter. It's called what? Matter. So what matter occupies, for example, what your body occupies wherever you stand, how much space do you occupy with the whole of your body? Now that is your volume. So the amount of space occupied by matter is called what? Volume. And the SI unit of volume is cubic meter. Meters cubed. Cubic meter. Correctly read as cubic meter. And the other units. Other units of volume include cubic centimeters, cubic millimeters, liters, and many others. Okay, but let's get familiar with this. Cubic centimeters, cubic millimeters, liters. But the SI unit, remember, dear student, is cubic meter, and this M is written as a small letter m. How can we convert 1 cubic meter to centimeters cubed, or cubic centimeter? 1 cubic meter simply means 1 times 1 times 1 meter. So, and we know that 1 meter is equal to 100. So it says 100 centimeters times 100 centimeters times 100. And we shall get 1 million centimeters cubed. So therefore 1 cubic meter is equal to 1 million cubic centimeters. Okay, but also remember that 1 milliliter is the same as 1 cubic centimeter. 1 milliliter is equal to 1 cubic centimeter. Is the one originally being called as cc, cubic centimeter, the cc. So 1 milliliter, even this one said a mil, no, it is a milliliter. 1 milliliter is equal to 1 cubic centimeter, and 1,000 milliliters equal to 1 liter. 1,000 milliliters is equal to 1 liter, implying that 1,000 cubic centimeters, equal to 1 liter. But 1 cubic meter is equal to 1 million cubic centimeters, or 1 million milliliters. Let's look at an example. Express each of the following volumes in centimeters cubed. These are the ones to express. Okay, now 27 millimeters cubed, or cubic milliliters. 27 cubic. Now, 1 cubic millimeters should be 1 times 1. This is a mistake. This should be millimeter. M. 1 times 1 to make 3. So, and now, how many centimeters are in a millimeter, or how many millimeters are in a centimeter? We know that 10 millimeters are in 1 centimeter. So if we are moving from millimeter to centimeter, so we divide by 10. So here we shall have 1 over 10 times 1 over 10 times 1 over 10. Okay, because 1 millimeter is the same as 1 over 10 centimeter. So but we have cubic, so we shall multiply 3 times. So therefore get that 1 millimeter cubed is equal to 1 over 1000 centimeters cubed, which is 0.001 centimeters cubed. So now if 1 is equal to 0.001 centimeters cubed, how about 25? Then we multiply by, rather, how about 27? Then we multiply 27 by 0.001 cubic centimeters, and we get the answer 0.027 cubic centimeters. Okay, looking at the second one, we saw that 1 meters cubed, 100 times 100 times 100, because this is 1 meter times 1 meter times 1 meter. In terms of centimeters, it is 100 times 100 times 100 centimeters, and of course we saw that we shall get 1 million centimeters cubed. So if we now have times 0.005, so we shall multiply this by 1 million, and we shall get 500 centimeters cubed. Okay, another example. How do we go now to meters cubed? Those two numbers, 9,000. Again, we saw 1 meter cubed is equal to 1 million. So now here it will mean that we shall divide the 9,000 by 1 million. Okay, and we shall get 0.09 meters cubed. Okay, how about 27? Of course, this now simply shows that you divide the value by 1 million, and we shall get 0.00027 meters cubed. Now let's look at the volume of regularly shaped solids. The volume of regularly shaped solids can be obtained by applying the appropriate formula. Now the table below shows some of the regular objects and their corresponding formulae for the volume. Now we're going to draw the table, and where we shall insert our objects so that we can look at the shapes of the objects. So we have here the object, and we have the volume formula, and we shall start with a cuboid. So I'm drawing here the shape of a cuboid or a box, like this one here, which has the dimensions length L, width W, and the height H. This is in the shape of a box. Now if it has all the sides equal, then it is called a cube, but if the sides are not equal, then it's called a cuboid. So how do you get the formula? How do you find the volume of this box here? And the formula is L, the length, times W, that is the width, and times the height H. So simply L times W times H, which is length times width times height. And let's also look at something different, which is cylindrical. How do you get the volume of a cylinder? Now the cylinder has a circular surface of radius R and has a height H if it is vertical, but if it is horizontal, then this H can be taken to be the length, and we shall take that to be L. So the formula is given by pi r squared H. V is equal to pi r squared H. Now the pi r squared here, you know, this formula of pi r squared is the area of the circle. Now this is the area of this circular surface here, or the area of the circular surface. So we multiply this area by the height, so pi r squared H times height, and we get the volume of the cylinder. Let's look at other shapes. Continue drawing in our table here. We're going to look at a triangular prism. Which takes that shape there. Which takes this shape. Now the base of the prism is rectangular. We have the width W and the length L. So this triangular prism, how do we get its formula, how its volume? We shall just get the base area, the area of the base times the height, the base area times the height. So for this case, what will be the area of the base? W times L, or length times width. We shall get the area of this rectangular base times the height, then you get the volume. If the prism has a triangular base, if for example you changed it and has a triangular base, then you just get the area of the triangle times the height, depending on the shape of the prism. But for this case, it has a rectangular base, so it is LW times height. And let's also look at the sphere. A sphere is something which is spherical. It's like a ball, a ball, basketball, netball, football. Those are spherical objects, and they have radius R. So the formula for volume of a sphere is given by 4/3 times pi r cubed. 4/3 times pi r cubed, or simply 4/3 pi r what cubed. This is the formula for volume of a sphere. Now let us look at examples. Example 1, a block of glass 5 centimeters long, 4 centimeters thick, and 2.5 centimeters high. Calculate its volume. That block, we can see it is it is going to be in the shape of a block or a box. So we shall just say L times W times width, and we get 5 times 4 times 2.5, and we get our answer as 50.0 centimeters cubed. The units are in centimeters. Example 2, find the volume of a cylindrical tin, 7 centimeters, radius 7 centimeters, and the height 3.0 centimeters. Again, in our solution, the area of the cross section, which was the pi r square times the height. So we shall have the pi is 22/7 times radius squared, which is 7 times 7 times 3, and we get our answer as 462.0 centimeters cubed. I go further to other shapes. Triangular prism. If B stands for breadth, height, that's the height, and this is L. So we say that we shall get the cross-sectional area, or the base area, times the height, and the area we shall say, if it is a triangular prism like the one we saw above, we remember we just use this formula: 6 times 5 times 12, and we get 360 centimeters cubed. And lastly, let's look at the fourth example here, also about the sphere. Find the volume of a sphere whose radius is 3 centimeters. Of course, remember, say the formula is 4/3 pi r cubed. Just substitute, and we shall say 4/3 pi r cubed. Now the 4/3 pi is 22/7. It can also use 3.142 times 3 times 3 times 3, which is cubed, and we shall get the answer as 113.14 centimeter volume for the sphere. Now those are solids. Can we now look at measurement of volume of liquids? Measurement of volume of liquids. Now liquids have no definite shape, you know that. but assume the shape of what? Of the container in which they are put. So liquids assume, or they take the shape of the container in which they are put, and therefore one of the methods which we can use to measure volume of liquid is to pour the liquid into a container with a uniform shape or a uniform cross-section area as shown in this figure below. For example, now if you pour water in this and the cover is up to here, now since this is regular, this is in form of a cuboid, so we can find the volume of this liquid by taking the length times breadth times the height of the liquid. Okay, so a container with a regular base and the height of the liquid is h is measured. So this height is measured and this measured, the length and the breadth are also what? So the volume of the liquid is then obtained by applying just the formula, which is the base area times the height, which is area A of this base times the height, or L times B, which is this L times this B, and therefore the volume of this liquid here in this container will be LBH. LBH. But we can also use instruments to measure the volume of liquids, and which you know them. We have measuring cylinder. Measuring cylinder here measures in milliliters or milliliters. Remember, 1 milliliter is the same as 1 centimeter cubed. So this is a cylinder, measuring cylinder. We have a pipette. A pipette only measures a certain quantity, like this mark here, calibrated mark. If they say this one is up to 10 milliliters, it means that when you suck the liquid into this up to this point, those are 10 milliliters. Then you have what we call conic flask or volumetric flask. Also has a calibration or a mark which shows that if it is 100 milliliters, that means when you pour the liquid up to here, it will be 100 milliliters. These ones have fixed volumes. A pipette and a conic flask have fixed volumes. You can have a beaker. A beaker also measures volume of liquid. I'm sure you have ever seen a beaker, either plastic or glass, as long as it is calibrated, marked. Okay, it's calibrated from here 50, 100, 150 milliliters or cubic centimeters. Then there's another device called a burette. A burette has the marking running from up here going downwards, increasing, but also measures the volume of liquid. So these instruments here measure the volume of liquids accurately. Now, before we want to look at the experiment to investigate the relationship between volume and height. Experiment to investigate relationship between volume and height. Now here I have two. I have this and this measuring cylinder P and this measuring cylinder Q. The procedure: take two containers as I've showed you, P and a Q, with regular base and cylindrical base respectively. Container Q is calibrated, which is like a measuring cylinder. Pour some water into P and find its volume V. So after you've poured in that, you can find the volume, transfer the water from P to Q and record the height of h of the water in Q. Repeat the experiment for different values of the volume, and each time record the corresponding heights when you have poured the water in Q. And then from there you record your results. What volume did you get? What height did it give you? Divide the volume by the height. When you divide the volume by height, then it means you are finding the area, because we say that V is equal to area times height. So when you divide the volume by height, you are getting what? The area. So you draw a graph of V against H. The graph is a straight line, indicating that the height increases uniformly with the increase in what? In volume. Okay, that the height increases uniformly with the increase in volume. That's a simple experiment you can work out to see how the height changes as you increase the volume of the liquid. So in practice, it is convenient to make measuring vessels in cylindrical form, marked in such a way that volumes can be read off directly. So instead of us continuing to first calculate the base area and then measure the height, so you can do that by simply calibrating or marking the cylinder. So measuring devices which are marked off like this one, like the one I'm talking about, when it is marked, it's called measuring cylinder, or they are called measuring cylinders. They are used to measure the volumes of liquid, or the volume of liquids. Measuring cylinders are made of glass or transparent plastic and are graduated. Simply means they are marked in cubic centimeters or in milliliters. Now measuring flasks, pipettes, burettes and beakers can also be used to measure volumes of liquids, or the volume of liquids. Measuring flasks and pipettes are used to transfer known volumes. Like I told you, a pipette which is 25 milliliters, it means it can only transfer 25 milliliters. A conical flask of 100 milliliters, it means you first pour and you get that 100 up to where there's a mark. The burette delivers volumes of up to 50 centimeters cubed. Okay, of up to 50 centimeters cubed. That is a burette. Now you should need to note that the scale of the burette begins from 0 at the top and increases downwards to the maximum value. For example, a reading of 31.0 milliliters or cubic centimeters on a burette means that the volume of the liquid poured from the burette is 31 milliliters, and the volume left in the burette is 51 minus 31, and we get what? 20 milliliters. I want also to note that while using the measuring vessels, the reading of the volume is taken with the position with the eye positioned level with the bottom of the meniscus. I'm going to show this in the figure below. Now this is what I'm talking about. Now water, for example, has, when you pour water in a liquid, it appears here. Its meniscus is at a lower point. So when you are reading you're taking the reading at this point, you don't have to look at the top here, but you have to look at the lower surface of the meniscus. The eye is level with the bottom of the meniscus. So, and then you read this value. Like for example, for this value, if this is 20, 21, 22, 23, 24, but not 25. So the volume of this is 24 centimeters cubed. 24 centimeters cubed. When you're taking readings for water, you read the lower meniscus. Okay, now let's look at measuring the volume of an irregular shaped solid. Volume of an irregular shaped solid. We looked at the ones which are regular, which have sides that can be measured. So volumes of regular solids are measured using the displacement method. The method works with solids that are not soluble. Remember that in water. This method works with solids that are not soluble, do not absorb water, or do not react with water, and should sink in water. So determine the volume of an regularly shaped object. We can use the displacement method, and that we can use, first of all, we can use a measuring cylinder alone. When you are using only measuring cylinder, you need a stone. Like for example, want to look at volume of a stone, you need a thread, and then you need a Eureka can, which is no, you don't need a Eureka can for this, but just measuring cylinder. So here I'm showing you, before placing the stone, water is poured in a measuring cylinder, and the value of its volume V1 is red. Maybe let's call it V1. Okay, and then the stone is tied on a thread and gently lowered into this. Now it will displace the water, which was initially at V1, to rise up to a value which is V2. Okay, so this water will be displaced and it will rise up and go to a higher height, whose volume will be read as V2. Okay, so now how do we get the volume of this stone? Now simply, now we subtract V2 minus V1, because this volume displaced, it displaced the water. It displaced the water. So the procedure I've just been explaining. Partly fill a measuring cylinder with water, that's partially or halfway. Note the volume V1 of water. Tie a stone that can be fitted into the measuring cylinder with a thread and lower it gently, so that water does not spill out. Lower it gently into the cylinder until it is fully submerged. Ensure that there are no air bubbles surrounding the stone. Record the new volume, which is V2, and the volume of the stone is given by V2 minus V1, just as I've said before, V2 minus V1. Good. How about using a displacement can, or the Eureka can? A Eureka can or displacement can is a container with a spout from the side. It is used to measure volumes by displacement method. It is also called an overflow can, and here it is. This one with this spout here is called the Eureka can. This is the Eureka can. Okay, so now what do we do? First pour water into the Eureka can until it flows out, through the spout. When it has stopped flowing, then place the beaker under the spout, because now it will be at this level. The water will be at this level here. So now place the beaker under this spout here. Before, the beaker should not be there. First pour water in this beaker until it overflows. When it has stopped overflowing, it means it has reached this level. So it means now that you can now place the beaker under an empty clean beaker under the spout, which is going to collect the water that will be displaced when you place there the irregular object. So the stone is tied on a thread and then gently lowered. Now as it lowers, it displaces the water, and the water is collected in the what? In the beaker, and the water is collected in the beaker. So the volume of water collected here in the beaker, it means it's the volume which was displaced by the stone, and therefore it is the volume of the stone. Okay, so procedure: fill the Eureka can with water until it flows out of the spout. Once the flow has stopped, place a measuring cylinder under the spout of the can. Okay, tie the solid whose volume is required or you want to determine with a thread and lower it gently into the can until it is completely submerged. Again, lower it gently, because let the water not spill out, or don't just throw it in there and then the water also jumps out of. There will be some errors. So the volume of water collected in the measuring cylinder is the volume of the stone, the volume of the object that has been submerged. That is a simple experiment you can do, or you can determine the volume of an irregular object. Good. Yes, having looked at that volume, have known how do you get volume of a regular solid, how do you get volume of an irregular solid, and how do you get volume of liquids. So let's now look at another physical quantity. Let's look at another physical quantity, mass. Okay, let us look at another physical quantity, mass. Now these are masses. I think you have ever gone to buy sugar to a shop, say 1 kilogram of sugar, then they use a weighing scale, they put there this stone, 1 kilogram. I'm trying to show you also here that these are masses that are used in physics lab. Later you will meet these masses when you're in the physics lab to kind of carry out experiments with masses. So the concept is about mass. Okay, what is the amount of matter in a block of wood, a lump of sand, or a heap of stones? What amount of matter is in there, into some object, into anything, any block of wood, sand, lump of sand, or heap of what? Of stones. So the amount of matter in each of these materials is called mass. So that amount of matter in these things, sand, wood, a wall, anything, mention them. Even in your body also, that amount of matter is the one we call mass of a body. So mass is the quantity, not if. Mass is the quantity of matter contained in the body. So mass is a basic physical quantity, and the SI unit of mass is a kilogram, as we told you earlier in the introduction. So mass is a basic or a fundamental physical quantity, with its SI unit being a kg, a kilogram. But the other units of mass bigger than a kilogram or smaller, we have gram, G, we have milligrams, we have tons or tons, and we have metric tons, MT, we have pounds. Some countries use pounds, LB. We have stone. Yes, there's a unit of mass which is called a stone. We shall see the conversion later, but for now I'm sure you are familiar with gram, milligrams, tons or tonnes, metric tonnes. Okay, so when you look at the conversion of units of mass, let's have this table. 1 kilogram is equal to 1,000 grams. 1 ton is equal to 1000 kilograms. A ton, 1 ton is equal to 1000 kilograms. But 1 pound is just not even a half a kilogram. It's about 0.45 kilograms. 0.45 kilograms. Then 1 stone, some countries use stone as a unit of mass, is equal to 6.4 kilograms. And then for smaller ones, 1 gram is equal to 1000 milligrams, and 1 gram is equal to 1 million micrograms. You have to master this that you are aware. Examples: convert the following units of mass to kilograms. For example, just have these simple numbers here. 5 tons to kilograms, 8,400 grams to kilograms, 54 pounds to kilograms, 560,000 milligrams to kilograms. Let's start with number 1. We say that 1 ton is equal to 1000, and 1 ton is equal to 1000 kilograms. So how about 5? Shall say 5 times 1000, and we shall get, hence 5 ton is equal to 5,000 kilograms. Look at the second one. $84,000 grams into kilograms. 1,000 grams. Now we have 1,000 grams equal to 1 kilogram. How about 1 gram? It will be the same as 1 over 1,000, 1 over 1,000 kilograms. So when you substitute about 84,000, 1 over 1,000 times 84, and we shall get our answer to be, if you simplify this, you can get the answer. I have not calculated it out, but you can get it. But simply you can see that these zeros will cancel with this 0, and we shall have 84 kilograms. About 54 pounds. We said 1 pound is equal to 0.45. So 54 we shall just multiply by 0.45, and we get hence 24.3. Yeah, so when you get a unit like pounds, don't get surprised. At least now you have learnt it. A pound. Milligrams to kilograms. 1,000 milligrams equal to 1 gram. So, but 1,000 grams equal to 1 kilogram. So we shall multiply 1,000 times 1,000, because this is smaller than this. 1,000 times 1,000, applying 1 million milligrams is equal to 1 kilogram. How about this? So we shall divide by 1. Supposed to be divided by 1 million. There's an error here. Supposed to divide this by 1 million, and the answer will be 0.56 kg. This should be 1 million. So that's how we convert units. But we will meet an exercise where we will practice on more numbers or more values of converting units of mass. How is mass measured? Mass is measured using instruments used to measure mass of a body. Of course, you are aware of them. There's a weighing balance or a beam balance. beam balance here, okay, where the kilogram stone is put here, and then what you want to weigh is here. When they balance, then it means that what is on this side, the mass on this side is the same as the mass on this side. These are called lever scales. Lever scales can have here maybe 1 kilogram, 2 kilograms, 5, a half, maybe a quarter. You have ever seen these stones of a weighing scale? Another instrument is a triple beam balance, which is mostly commonly used in the chemistry lab. Have a triple beam balance. Triple because it has 3 scales: this scale, this one, and this one, which help to determine the mass of certain compounds. Then there's an electronic balance. This one is connected to power supply and gives digital values of whatever I put here. The mass is given here. And we have spring balance. Spring balance, we have this one, which is they are hanged always up, and then the substance to be measured is hanged on this hook, and then there's a scale. There's a scale here. For example, if they're measuring beans, this one should be held firmly upwards, and then whatever is measured to be measured is suspended by this hook, and then this pointer will move to give you the value of mass. Yeah, there are so many like compression balance. Instead of hanging, you can have this one where you place something on top of here and the meter moves. Okay, the spring balance, I've talked about that. Compression balance, I've talked about it. Then there's this one called a lever balance. Yes, have these marbles here placed here, and this pointer will move from 0 up to when the mass is the same as the one which is placed on the pan. So those are different instruments. There are different instruments used to measure mass, which I feel you have seen some of them, but if you've not seen others and you meet them at school, maybe in the labs or somewhere, you'll be curious. Even when you're moving in a supermarket, when moving somewhere in a market, be curious to spot out some of these weighing scales. Okay. Lastly, let us look at measuring time. And what is time? Time is just a measure of progression of events from the past through the present to the future. You look at how events have been changing from past to the present, through the present to the future. Time is a basic physical quantity. In international system, the SI unit of time is a second, and we use symbol S. Is a second, and we use symbol S. But there are other units that you are aware. If I may ask, what are other units of time at your fingertips? You can give me the answers. We have minutes, we have hours, we have days, we have weeks. Many more. We have months, we have years, and increase the years, we have decades, jubilee, century, a millennium. All these are units of time. And when you advance, you later see that time is also measured in terms of light years, which I have not put here, but that one at an advanced level, light years. So, but smaller divisions of a second include microseconds, milliseconds, all these are units of time. How is I can convert? I just give you a table, but you can convert this later. So how many seconds are in 1 minute? We have 60 seconds. How many minutes are in 1 hour? We have 60 minutes. These are obvious, you know them. 1 day has how many hours? 24 hours. 1 week has how many days? 7 days. And 1 year has 365 days. But there is a month which may have February may have 29 days, and then we shall have 366 days. 1 decade means these are 10 years, and we have 1 second is equal to 10 times 1 times 10 power negative 6 microseconds. But now we shall look at the conversions of those units in your exercise. I don't want to look at the examples of this, but you can do some exercise about converting units of time. How is time measured? In the ancient days, different ways were used to measure time. These include observing the shadow, flowing sand, heartbeat, and corkscrew. Many of these methods were, however, inaccurate and unreliable. For example, somebody would just monitor the shadow of a tree and say, if it is here, then it is 8 a.m. If it is here, it is noon. If it is here, it is 4 p.m. Then it is 6. But those were estimations and were not accurate. Nowadays, engineers have developed more accurate clocks for measuring what? Time. Remember, when you're studying physics, you can become an engineer and you specialize in physics. So those who specialize in physics have developed clocks, they have manufactured clocks that can accurately measure time in these modern days. Okay, so but let me just give you some pictures of the ancient instruments used. There's this one, is called the hourglass. Hourglass, it would have sand here, or would have sand or water. It's called hourglass. And then there is one which is called the sundial. The sundial was an ancient instrument used to measure time. And many others. There is also a candle dial, a candle clock, where they would put a candle inside here and keep monitoring it, and that is called that is also an ancient instrument which we no longer have in these modern days. We are just enjoying the modernity of instruments, which I'm going to look at. Wow, now there's this one here, a wall clock. I guess you have one in your room at home and you are using it to measure time. That is a wall clock. I believe that you know how to read the time at this level. You can't be taught to read time. You should be now knowing, because that is P2 work. That's a wall clock. Then in the physics lab we use a stop clock. In the physics lab we use a stop clock which measures time intervals. It's not just to measure. This one will measure time intervals. You can keep timing. Maybe the oscillation of a pendulum can be timed using a stop clock. This one here. Then there's a hand watch. Yeah, the hand watch. I guess you have this one. You have ever bought the watch for yourself to time yourself. It's an instrument for measuring time. And then the dicto watches. Dicto watches. They can be a hand watch, but giving dicts. The word dicto comes from dict, so gives you the dict directly. So these are dicto watches which are used to measure time. Especially these ones are always on gadgets like on a woofer, on a decoder, which you use maybe to play. For example, this tutorial, you find that there is a dicto timer there. Okay, a dicto timer, a dicto watch or clock. Then there is a dicto stopwatch. This is a stop clock and this is a stopwatch, where you press to start and to stop. These ones are always used at sports grounds, especially to time person running from one end to another, like pro teach those who go to compete. The Bolton, the Bolt, Hussein Bolt, not Bolton, Hussein Bolt, Kiprotich, Kipsiros, our athletic legends here in Uganda. When they go outside there, even us here when we're at school and we need to use these watches to time, these dicto stopwatches to time ourselves. So these are modern instruments which have made life so easy. So these days there's another one which is called a smartwatch, which does more things than just timing. It does so many other things. Smart, like a smartphone. It's being smart. Calling it smart is not that it's nice looking or what, but it just does several things in one thing. So we also have the smart watches, but the most important bit, what I'm talking about for now, is a watch or a clock to measure our physical quantity, time. Of course, even phones have dicto watches. They show the time. These days, even some of us don't even buy watches, we rely on those ones on the phone, but they are dicto. So that is, these are the modern instruments for measuring time. So how many physical quantities have we looked at? We've looked at length, we've now looked at area, we've looked at volume, we've looked at mass, and we have looked at time. Now a simple home work that I want to give you, that you need to work with a friend, is need to do some work with your friend. Just go to a field, nearby field, and again do something which is a pendulum. Tie a stone on a thread, and that will act as a pendulum. So what you need a clock or a watch and a pendulum. You can use it, even your phones have those stop clocks or dicto stopwatches. So you must work outside with two friends and mark out a short distance, about 100 meters. You can run. A good idea is to run across a football field. One of you will run the distance, the second will estimate the time taken using a pendulum, and the third will measure the time taken using a clock, so that we have it accurately. Do this 3 times so that each of you has a chance to run, estimate, and measure. Do the experiment several times to see if you can get an estimate. You can get better at estimating time. Record your results in the table like the one below, where you're going to have the name. Okay, you have the name, you put in the name here. This name is supposed to be here. Have the name here, then you have here accurate time using a stop clock, and here the estimated using what? A pendulum. Now how do you estimate using a pendulum? When a pendulum oscillates to and fro, moves from here, comes here, then it goes back, that is going to be, you take that as 1 second. 1, 2, When it goes and comes back, that one is 1 second. So you count 1, 2, 3, 4, 5. So then you count the number of seconds that from the time a friend started running up to the point when I stopped in the distance which was what marked. So that one, then you compare it with the accurate one, which will be measured using a stopwatch, either on your phone or you can buy one. They are very cheap, they are not expensive. So with that, we shall proceed from here and look at another physical quantity, which is density, next time. But I want to encourage dear student who has obtained a tutorial to always reach us through the contacts below and be able to access assignments where you will be marked virtually, such that you evaluate yourself as you progress, other than just watching the physics tutorial as if you are watching a movie. I encourage you and encourage your parents